Hello AP Chemistry and welcome to 4.3 Acids and Bases. So this is a very brief introduction to acids and bases. We will spend, I believe, 3 chapters later on this year talking about it. So, we're going to talk a lot. And it does build on the stuff we talked about last year, right? So it is assumed knowledge that you're able to calculate the pH of a strong acid or a strong base solution, right? You are also able to calculate the pH of the solution after a strong acid and base react, for example. So make sure that those are things that you can do, and if need be, come see me sooner than later so we can chat about that to make sure that you will be successful. All right, so first, what is an acid? So most commonly, we are going to talk about that as something that is a proton donor, right? And if we think back to last year, right, protons in this, when we're talking about it, right, are H pluses, right, which protons are accurate for that because hydrogens come with 1 proton and 1 electron, and if we lose 1 electron, right, such that it has a positive charge, then really it is a proton at that point, yes? So proton donors. Now, obviously acids can be as simple as HCl, for example, where it's clear, right, that this ionizes in solution to form H plus ions and chloride ions. A lot of acids are not that way, right? There are a whole range of organic acids that don't look like that, right? Which is why we need to differentiate, right, between an acidic proton and a non-acidic proton. Your book last year talked about acetic acid as being an example. Here we have an acid, right? And we have these groups, right? These COOH groups, right? So if we think about this, so if this is an H, this is an H, right? This is the C and everything else, right? Here we have COOH, right? And now, what that means is the acidic proton is this one, right? So this whole group is referred to as that COOH, right? Or so this part makes this compound a carboxylic acid, right? And so that's a common functional group, right? Or common thing we'll see added to organic compounds, right? Where what happens is that those oxygens, these oxygens, pull electron density away from this hydrogen, right? Which means that this hydrogen then becomes more positive, right? More partial positive, and it's able to be taken by a water, basically, right? So anyway, this is our acidic proton, right? But note that there is this abundance of other protons that are not acidic, right? So for example, if we were going to write a reaction of this with some strong base, right, we wouldn't just take away all the H's. We would only take away the acidic H's, right, the ones that are part of a carboxylic acid group. Yes, does that make sense? All right, so then this acid in particular, right, has 3 acidic protons, to be clear, okay? When we're talking about bases, right, so bases, for the most part, right, are going to be our soluble metal hydroxides, okay? Our soluble metal hydroxides, which means that obviously, you got to know your solubility rules, right? But basically, that's just group 1 and the bottom part of group 2. Those are our soluble metal hydroxides. And those are our strong bases. But then there's a whole world of organic bases, right? Which, broadly, the ones we're going to talk about most are amines, okay? Where amines are any nitrogen stuck to 3 things, right? The most common of which that we talk about would be this one, right? Which I don't know if you remember, but from last year, this is ammonia, right? That's NH3, and if we think back to what nitrogen tends to look like when it forms Lewis structures, it's a nitrogen stuck to 3 things, and it tends to have a lone pair. This lone pair is what allows it to be a base, because if acids tend to be our proton donors, bases, by the definition we're going to use most of the time, right, tend to be proton acceptors, right? And in order to accept a proton, it's got to have a lone pair to do that, right? To form that new bond with that H plus, because it doesn't have any electrons to bring to the table, right? So ammonia. And note that these could be H's, right? Or those could very well be anything, right? Sometimes they're symbolized with R's if they're carbon-containing groups, right? But either way, nitrogen stuck to 3 things are our amines, right? Which means there's a lone pair, which means it can accept a proton. All right, now, acid and base strength, right? You have to memorize this, okay? Please just memorize this right now, and you will be so much more successful over the course of the year because the math for how we solve for pH, the math for how we do reactions, right? All of that depends on whether or not something's a strong acid or strong base. So once you've got that memorized, it makes life so much easier. So please, I urge you, memorize this now. Note that little exception in your book, right? Sulfuric acid, only that first deprotonation is considered a strong acid, right? Like, so H2SO4, right, to HSO4 minus, right? So the loss of that first proton is the strong acid part, right? And then here, going back to electrolytes, right? So strong electrolytes are things that dissolve and then dissociate completely into ions, right? So, right, all of our strong acids are strong electrolytes, right? So again, we wouldn't know that connection if we don't know our strong acids, right? And our weak electrolytes, this makes up the most of what we're going to talk about in the land of weak electrolytes, are our weak acids and our weak bases. Yes, weak acids and weak bases make up our weak electrolytes, which means that if we go back to that picture right here, there's actually something in between here that would be our weak, right? Wherein it wouldn't be as bright as something that, say, well, like sodium chloride, but it also wouldn't be off. Yes, there is a land in between where we could differentiate that this is a weak electrolyte, because the light bulb would turn on, but not as brightly, okay? Now, when we talk about weak electrolytes in the land of net ionics, we will always just consider these to be molecular. Like, we will not dissociate them when we write a net ionic. Okay, so we will not dissociate them in a net ionic equation, right? And that tends to be one of those really common, like, simple errors that people make because that shows up all the time. So do be mindful about that. All right, so here is just practice 4.5 from your book. I just wanted to talk about this a little bit because your book words the question a little bit weirdly, and I just want to make sure we're all crystal clear here. So it says, imagine a diagram showing 10 sodiums and 10 hydroxide ions, right? So basically we had 10 sodium hydroxides that we dissociated. Okay, if this solution were mixed with the one pictured above for HY, specifically, I don't know why it asks for that one, what species would be present in a diagram that represents the combined solutions afterwards, right? So hopefully you thought that was pretty easy, right? Because if we count, right, let's do a count here. So we have 1, 2, 3, 4, 5, 6, 7, 8, right? And the matching number of protons, right? So we have 8 HYs, yes? And if we have 8 HYs and we have 10 NaOH, right, then it's easy to see, right, that we will react all 8 HYs, right, and we have 2 NaOH remaining, right, and we will have produced 8 H2Os. Yes, does that make sense, right? In the land of, I shouldn't put an arrow there, of what's happening, right? But thinking about all the rest of these, they're all the same scenario. Yes, as in HZ, we also have 1, 2, 3, 4, 5, 6, 7, 8, right? We would get the exact same outcome in HX, HY, and HZ, okay? The only difference is that the rate of the reaction will differ, which you'll be able to explain to me in a few chapters. But the end result, like what's in the beaker at the very end, would be the same for all 3 scenarios, right? And the key here is that strong acids and strong bases react completely, yes? As in this 10 hydroxide ions will react to the fullest extent possible, right? We're going to talk later about shades, right? Because not everything reacts to the fullest extent possible, right? But strong acids and strong bases do, which means that all 10 of those hydroxide ions will react with a hydrogen ion if there are any available. Yes, does that make sense? All right, strong acids and strong bases react completely, always, always. All right, which means that all 3 of these scenarios would be the exact same. All right, thank you for listening. Be good, and I will see you soon. Stay tuned for redox.